A sheer vertical geological environment offers no natural accommodations for the human body. Moving upward across hundreds of feet of exposed granite requires absolute isolation. Free soloing is the strict practice of ascending technical rock terrain without any protective equipment, safety gear, or ropes. If the climber's grip fails, gravity dictates a terminal fall. A successful free solo ascent is the execution of a highly calculated biomechanical and neurological equation. There is a physical paradox at the core of this discipline. Strictly from the standpoint of physics and energy expenditure, climbing a rock face without a heavy safety rope is more efficient than traditional roped climbing. This efficiency relies on a severe biological caveat. The human system must actively suppress its own evolutionary survival instincts to maintain physical control. The free soloist survives by optimizing their anatomy to operate in an environment with an absolute zero margin of error. To understand this optimization, we examine the micro-level interface between the climber's shoe and the rock face. This split-screen diagram compares two interactions. Left, edging, directing vertical force onto millimeter-wide crystals. Right, smearing, maximizing rubber surface area against smooth rock. Modern vulcanized rubber compounds maximize the coefficient of friction, locking the foot onto near-vertical inclines. To achieve this precision, aggressively curved climbing shoes force the human foot into severe supination. Supination rolls the foot outward, shifting weight from the sole. Inside the curved shoe, load vectors concentrate on the big toe's distal phalanx. This posture bypasses the metatarsophalangeal joints, absorbing the climber's entire weight on a single point to maintain static equilibrium. Structural stability on the wall is achieved by intentionally overriding and distorting the foot's natural biomechanical weight distribution. Moving up the anatomical chain to the upper extremities, the mechanical tolerances become even tighter. Consider a hand gripping a razor-thin rock flake. Upward progression on a sheer wall is primarily limited by the biomechanical yield strength of the fingers and the forearm muscles controlling them. To hold the smallest edges, climbers use a technique called a closed crimp. This grip sharply hyperextends the first knuckle while heavily flexing the second, transmitting extraordinary physical force directly through the small phalanges of the fingers. This clinical schematic of a closed crimp isolates the A2 and A4 pulleys, thick bands of fibrous tissue acting as essential mechanical fulcrums. In a steep climb, epidemiological data shows these specific pulleys must sustain up to 450 newtons of force. Exceeding this structural tolerance results in immediate mechanical failure, specifically pulley ruptures or deep tears in the lumbrical muscles of the hand. In a free solo scenario, a localized tissue failure in a single finger pulley translates immediately to a fatal systemic failure. Removing the safety gear reduces the physical exertion required to climb. To see why, we must look at the mechanics of traditional climbing, commonly known as trad climbing, where a safety rope is used. Trad climbing requires carrying a heavy metal gear rack, stopping mid-route to manually wedge protective hardware into the cracks of the rock face. On the left, a trad climber's isometric lockoff rapidly depletes endurance while searching for placements. Conversely, the soloist operates with minimal mass and zero pauses. On the right, the soloist utilizes a continuous kinetic chain, transferring momentum smoothly from hips to shoulders to move upward. Because there is no interruption to place gear, this continuous momentum makes the physical movements vastly less taxing on the muscular system. By stripping away the safety rope, the soloist physically optimizes the climb, trading muscular endurance for an absolute zero margin of error. Surviving that lack of margin requires shifting focus from external biomechanics to the internal control system, the climber's brain. This cross-section of the human brain isolates the true barrier to free soloing, neurological panic. Here we see the amygdala, a small cluster of neurons in the medial temporal lobe functioning as the primary threat response center, reacting to extreme height and exposure. The amygdala rapidly triggers autonomic fear responses throughout the body. Heart rate spikes, palms sweat, and tunnel vision sets in. In a climber, this autonomic panic response degrades fine motor control, destroying the precise biomechanical tolerances required to grip the rock. Soloists actively suppress this response through exhaustive preparation. They rehearse a specific route dozens of times using a safety rope before attempting it free. This conditioning physically reprograms the brain, lowering the amygdala's sensitivity to fear stimuli. During a flow state, the prefrontal cortex sends inhibitory signals to calm the amygdala, suppressing biochemical panic and allowing for clinical, uninterrupted movement. The soloist deliberately suppresses evolutionary survival instincts to achieve this degree of neurological control. Pulling back, we see the climber as a complete, optimized biological machine in motion. Successful free soloing exists only at the exact intersection of optimal frictional coefficients at the feet and maximum anatomical tensile strength in the hands. Maintaining this delicate physical state is impossible without absolute neurobiological control over the brain's fear centers. While the physical exertion is mathematically highly efficient, the consequence for a single miscalculation remains absolute. In this diagram, as the environment fades away, we see the reality of the ascent. At this level of execution, the rock wall is reduced entirely to pure mathematics and physical forces. The soloist survives by aligning their physiology perfectly with the geological environment around them. Free soloing is the maintenance of this absolute calibration. Survival depends on the flawless, continuous operation of the biological system within these narrow physical limits.